Hello everyone, good afternoon. Myself Ankita, Industry Relationship Coordinator at Takshila VLSI Institute Technology. Welcome to today's VLSI webinar. Before I start, I would like to give a brief introduction about our institute. The Takshila Institute is a leading VLSI training center in Bangalore and Hyderabad. We offer special courses help you learn important skills in VLSI field. We offer physical design, analog layout design, analog circuit design, ASIC verification, and design for tests. Why to choose Takshila? Here are some of our unique features. We provide 24-bar tools access and VPN support to candidate to practice. Hard copy materials are provided to enhance your learning experience. Experienced trainer. Our trainer have more than 5+ years of experience in VLSI industry. Placement support. We offer 100% placement assistant until you get a placed in VLSI semiconductor industry. Our candidate had successfully got position with leading companies such as Micron, Cadence, InSemi, OnSemi, HCL, AMD, Capgemini, etc. Today's webinar will be presented by Neha ma'am. Ma'am have a 5+ years of experience in VLSI industry and currently working as a physical design engineer. Now I will hand over the session to Neha ma'am. Ma'am will continue the webinar. Thank you.
So good afternoon everyone, I'm Neha. So I'll be taking today's webinar session for you. So as you can see here, our webinar topic is job opportunities in VLSI or the semiconductor industry. So we'll be dealing with the whole industry. So an introduction to the semiconductor industry as well as the different design flows and the placement opportunities, the eligibility criteria, the core job opportunities, everything we'll be discussing in today's webinar. So this is our agenda for today. So as I said, we'll be discussing these topics today. So you can see all the topics I mentioned earlier. And finally, we'll have a Q&A session. So if you have any doubts regarding any of these topics, you can ask me. Even regarding our institute, that is Takshila VLSI. So regarding the courses or the duration or anything, if you have any doubts, you can ask me in between or at the end of the session. So we'll start today's webinar. So before going deeply into the VLSI or the semiconductor industry, there are some terminologies that we should already know. So what is a semiconductor or what is VLSI itself? So semiconductor, you might have heard this word. So that is a material, semiconductor materials that conductivity comes in between a conductor and an insulator. So that will pass some of the currents through it, but not like conductor. So using these semiconductor materials, we are actually making something called the IC or the chip. So this is the chip that we are talking about. So this chip may be working for different functionalities or based on the applications, we are making or designing these chips. So the industry which deals with the designing and manufacturing of these ICs or chips, that is called the VLSI industry. And VLSI is nothing but very large scale integration. So very large scale means inside this chip itself, many number of elements might be there. So that might be transistors, resistor, capacitors. So many elements can be there inside. So based on the number of transistors or the number of elements inside one single chip, if it is in a very large scale, that is the number is very more, then we are calling it as very large scale integration. And that industry we are calling VLSI industry. So basically, this industry deals with the designing and manufacturing of the chips or the ICs. And IC is nothing but integrated circuit that you might know. And one more term is ASIC or application specific integrated circuit. So ASIC is nothing but that is also one kind of an IC, but it is designed or it is made for a particular application. Say for example, the IC is made for your mobile phones, so that can only work for your mobile phone. It cannot do any other functionalities like for cars or TVs or anything. It is particularly made for one application. So that kinds of ICs are called application specific ICs or ASICs. And when we talk about all these ICs or these chips, where we are actually using them. So that is in almost all the electronic equipment that we see today. It will contain one or more ICs inside them. Say for example, mobile phones, laptops, TVs, satellites, car, or anything. Even in your simple calculators you are using. So that also will contain a simple IC in them. So that is how we use these ICs that we are manufacturing in our VLSI industry. So that important is the IC we are talking about because it is almost in all the electronic equipment that we see today. And that important is the industry also. VLSI industry also, it is very important. And this is how the chip will look like from the interior portion. So you might or you might not have seen a chip actually, but it will look like fully black thing. So the black package that you see, it is just this plastic package. That is this one. Only this black color you can see, and these external pins also you might be able to see. But the actual IC or the chip is not that. That is placed inside. So this small square that you see, that is the actual IC or the chip we are talking about. So this IC should not be damaged or it should not get destroyed. And that is why it is kept inside this plastic package. So this IC is connected to these external pins using these wires. So they are the gold bound wires. So using these wires, we are connecting it to these external pins. These pins. So, and these external pins, we are connecting it to the external circuit. That is how the interior of an IC will look like. And this you see here is one term in the industry, that is semiconductor wafer. So in the manufacturing process of an IC, we'll manufacture it from something called this, that is the semiconductor wafer. So from one wafer itself, maybe hundreds or thousands of ICs are manufactured at the same time. So if you look closely, one small square that is here, that is actually one IC or one chip. So one individual chip is this small. All these are small individual chips. So all these chips, they are actually manufactured at the same time from one single semiconductor wafer itself. And the size of this wafer can also vary. So this is 12-inch wafer. So depending upon the size of the chip we want, this wafer size also will vary. So that is about the manufacturing of ICs. So the detailed manufacturing video, we'll see it later. So you will get a more clearer idea. Now we'll move forward. And when we talk about all these ICs or the chips, it was invented in around 1970s. So at that time, only 5,000 transistors we were using in one chip. But today, actually, we are dealing with 100 billions of transistors inside one single chip. So this is what we are talking about, transistor or a MOSFET. So this is a CMOS structure. So this transistor in hundreds of billions, we are actually like keeping inside one single IC. So you can see that like the huge increase in the number of transistors we are using. Why is it? Because the complexity or the application level or the functionality of the chip has been increased so much. Like from when it was invented to now, we can see how much technology has developed. So in order to make that happen, like the functionalities to happen, more functionalities we need means more number of elements also we'll need to implement that functionality. That is why the number of transistors has increased in the past years till date. And this increase in this number of transistor, like it is followed, it follows a basic trend, and that is called the Moore's law. So it was put forward by Gordon Moore, the co-founder of Fairchild Semiconductors. So what he says is that the number of transistors in a dense IC, it gets doubles in every 2 years. So that has been following in the past years. So if you take a close look at it, in 1970s, the number of elements was like thousands, 5,000 range. But, but in 2018, it got increased to millions and billions of numbers. So that fast is how the transistor or the number of transistor we are using in one single chip is increasing. And when we talk about the number of transistors in one chip, so we might actually wonder how we are including these many number of elements in one small chip. So, because the size of one chip is actually being reduced from the past till now, if you see, in the past it was the chip size was much bigger, but now the chip size got reduced. But when you look at the number of elements we are adding, that got increased. So, how is that possible? So, that is actually by reducing the size of each transistor in our IC. So in 1971, the size of the size of one transistor was 10 micrometer. But now we are dealing with 3 nanometer or 2 nanometer ranges. So difference is that 1 micrometer is 1 millionth of a meter and 1 nanometer is 1 billionth of a meter. So that small is the size of the transistor we are talking about here. So we have reduced the size from 1 micrometer to 1 nanometer. So it has reduced so much that we can include more number of elements because size of one element now we are increasing. So that more number of elements we can add. So based on the number of elements, it can perform more functionalities. So complex functionalities also can be performed with the help of more number of elements. So that is done by reducing the size of each transistor or MOSFET in our design. And when we talk about the size of one transistor, that is nothing but the technology node or the tech node. So this is one common term that we see in the industry. So there are different examples of technology nodes available. So you can see them here. So we select each technology node depending on our application. So if we like what application we are doing, we select which technology node we want. So technology node is nothing but the size of one transistor. And the size of one transistor, we can say it as the distance between source to drain of a transistor. So for example, that source to drain is actually the channel length, you might know. So if this is source and drain and this is the channel length. If gate is here means this is the channel length. So this channel length is actually called the size of one transistor. And that size is called the technology node also. And depending on that, different examples are there that are these. And technology nodes are available like even below 28 nanometer. And that is called the FinFET technology. So FinFET technology is a more advanced and more complex technology, and it is more fast also than the higher technologies. So how is it that the size of transistor is even more reduced? So like 3 nanometer, 5 nanometer, then 7, 10, 11, 14 nanometer, etc. So this is the most popular technology now, that is the FinFET technology. And we are dealing with these nanometer ranges in the industry nowadays. I mean, it is the popular technology nodes now. So that's about technology node. So this is how the whole semiconductor demand is divided between different end markets, or they are called the market drivers. So as you can see, majority of the semiconductor demand, it is used by computing as well as wireless communication purpose. So almost 64% we are using it for these two purposes. And then the next 14% is for consumers. So we are all consumers. Then the electronic equipment we use like laptops, etc. All those comes under this 14%. Then 8% each we are using for industrial and for autos purposes. Then the next 5% is for wired communication. Then finally 1% is for military and aerospace. So that is used by the government for aerospace and military purposes. So this is how all the semiconductors we are manufacturing it is divided across different applications or different industries or where it is used. So this chart was based on the application or the semiconductor demand. And this is how we are expecting the industry to grow in the next 10 years. So basically it is from 2023 to 2033. So in 10 years, how the industry is going to boom. So you can see here in 2023, the total industry was like 550 billion dollars. But in 2033, we are expecting it to grow maybe double or beyond that. So that fast is the industry growth that we are expecting because we have already seen the growth in the past years. So this fast was how it was increasing till date. But in the future also, we are expecting it to go beyond that growth. So that is what we call the industry boom. So we are expecting that the industry is going to grow like this in the future. So that many opportunities will be created and the VLSI industry will be growing so much more. So this graph shows the growth of our industry in the future. And this is one main topic when we deal with semiconductor or the VLSI industry. So that is the different companies that are available in the industry. So that can be basically classified or categorized into three. That is product-based, media companies, and service-based companies. So product-based is nothing but they design or they build their own product. So companies like Samsung, Intel, Qualcomm, Nvidia and all, you might have heard. So those companies are all the product-based companies. And when coming to EDA is nothing but electronic design automation. So the designing process of an IC, that is a completely automated process. So for this process, at different stages, we need different types of tools. So all these tools or the software and everything that is provided by the EDA companies. So they provide software and product based as well as the service based companies. They provide these tools. Then comes service based companies. So service based, as the name says, they just provide service. So they provide human resource to other companies. So they provide service to EDA companies as well as the product based companies. So that is how the industry is categorized into different companies, and all of them are actually called VLSI engineers, and all of them work together to form the VLSI industry itself. And now we have is a basic semiconductor ecosystem. So we have some example companies for different categories. So when we come to designing part, we have the fabless chip firms. So fab is nothing but where fabrication of the IC is happening. That is the manufacturing, physical manufacturing of an IC is happening at the fab. So some companies will have their own fab, but some companies might not have their own fab. So they are called the fabless. So they do not have their own fab. And examples are Qualcomm, MediaTek, Nvidia, Broadcom, AMD, etc. So they do not have their own fab, but they are also product companies. They design their own product. Then we have fabless non-chip firms. So examples you can see Google, Microsoft, Apple, etc. So they are also product companies, but their product need not be a chip. So that they are fabless non-chip firms. Then we come to IP and design software. So these are the EDA companies I was talking about. So they provide the EDA tools for the design purpose of an IC. And examples are Synopsys, Cadence, Siemens, ARM, etc. Then when coming to manufacturing side, we have foundries, and foundries are also like fab. It's a fab itself, where the manufacturing of an IC is happening. They are the foundries. Examples you can see: Global Foundries, TSMC, Samsung, etc. And in manufacturing itself, we have equipments. So we need different varieties of equipments for manufacturing of an IC. So all these equipments that are dealt with these companies like Tokyo Electrons, Applied Materials, etc. Then we have integrated device manufacturers. So companies like Analog Devices, Infineon, Micron, Intel, Samsung, then TI, etc. They are the integrated device manufacturers. Finally, we have testing, packaging, and assembly. So after the IC is manufactured, we need to test it properly. Then packaging should be done. Then assembling process is also there. So all this is done by these companies like Foxconn, Lattice Semiconductor, TER, etc. So this is the basic semiconductor ecosystem and some examples of the companies in the different categories. So now we move forward. And this is the list of the top semiconductor product-based companies according to 2023 ranking. So you can see Intel was the like top ranked, the top product-based company, followed by Nvidia, then Samsung, Qualcomm, etc. So you can see some of the familiar names in the list: Apple, AMD, Broadcom, MediaTek, Micron, TI, Infineon, etc. So this is just a list of the top product-based companies according to 2023. So these are the ED or the CAD companies. So we already discussed this, and some examples are Cadence, Synopsys, and Mentor Graphics. So EDA companies, as I said, they provide the tools, software access for the designing team. So tool is actually the most important part, we can say, in the designing of an IC. That is why I said that in different stages we need different types of tools. So that tools we are using that might maybe from Cadence or Synopsys or Mentor Graphics. So all of them will have different kinds of tools. So any of the companies, we can choose from any of the tools there, but we should take one tool. Like without the tools access, we cannot design an IC. So that is how we depend on the EDA companies for all these tools. And fab companies also we already discussed. So they are the foundries. So that is where the manufacturing of ICs happen. Examples you can see Global Found and in Global Foundries, TSMC, etc. And this also we explained that is the fabless company. So they do not have their own fabrication cell. And one example is Qualcomm. So a company who has their own fab, example would be Samsung. So they have their own fab so that they are manufacturing their own product from their own fab. So that is the difference between fabless company and companies with fab. So these are the top fab companies in the whole worldwide level. You can see the topmost is TSMC. And you can see other famous fabs like Samsung, Global Foundries, etc. So this is the worldwide top fabs or the foundries companies that are there. Yeah, so apart from all these product companies, then EDA companies, fab companies, etc., we have the service-based companies. So service based also can be divided into three. That is MNC service based, large service based, and startup service based. And some of the examples you can see: Capgemini, L&D, HCL, Tech Mahindra, Wipro. So that they are all MNC service based companies. Then in large service based we have Mirafra, Dassault, CRM Systems, Blue etc. In startup also we have so many companies. So like including startup and service based companies, there are like 500 plus companies spreaded in Bangalore and in Hyderabad. So we cannot provide the whole list of companies here because there are so many much more companies than this small list. So that is how the whole VLSI industry is divided between different companies. So as I mentioned earlier, we'll now see a short video on the manufacturing process of an IC. So this video is from one of the fab called Micron. We'll see that now.
Memory chip design is the first step in the production of Micron's memory chips. This process involves the use of computer-aided design tools to lay out billions of electronic components that store data on the chip according to the product design specification. During technology development, specific process steps are defined and integrated into a process flow that will build the memory chips. The process steps are tested and refined until the process node is qualified and ramped in manufacturing. Individual memory chips, or die, are built upon pure silicon wafers in a fabrication area, or fab. Fabs are state-of-the-art clean rooms that are 100 times cleaner than a hospital operating room to ensure silicon wafers are protected from ambient contamination. Among the many process areas in a fab, the photolithography area coats wafers with a photoresistant material. Then, like film in a camera, circuit patterns are exposed and excess material is rinsed away. The paths in these circuits are 5,000 times narrower than a human hair. Wafers are moved between different tools and processes using a robotic automated material handling system, or AMHS. Each wafer may be moved through more than 1,000 processes. It takes more than 1 month to make a memory chip. In probe, initial functionality tests are performed on each die on the wafer. A probe card positions probe needles onto each die to send and receive test data. This information is used to generate a map of all the die on each wafer. Only good die that pass all tests in probe will continue through the manufacturing process. In assembly, wafers are first thinned, attached to an adhesive backing, and then diced into individual die using a diamond edge saw. Using the wafer map that was created in probe, individual die are picked from the wafer, then placed on a circuit board. A solid gold wire is used to connect each chip to the circuit board. A molding process encapsulates each die in a protective plastic package and shipped to test. Every memory chip Micron manufactures undergoes hundreds of tests to ensure it meets the highest quality standards. Proprietary Ambix testers subject finished parts to extreme temperatures and conditions to force any weak components to fail before they reach our customers. Additional test equipment verifies that each part meets or exceeds its speed and performance specifications. All qualified parts are laser marked with part numbers and other identifying information. Each memory chip is optically scanned to verify strict fit and form specifications. Components are placed into industry-standard anti-static packaging and placed into boxes for shipment. Many of Micron's finished parts are used to build memory modules and solid-state drive. Automated surface mount assembly equipment is used to mount memory and other components to circuit boards. All products are tested using proprietary Micron module and SSD test equipment. Finished products are placed in anti-static packaging before boxing for shipment to the customer.
Yeah, so that was a short video on the manufacturing process. So I hope that was helpful. Now we'll move forward. So this is the eligibility criteria to get into the VLSI industry. So you can see basically anybody with a BTech degree or an MTech degree in these subjects like electronics, that is ECE, EEE, then ENTC, EIE, or MTech in VLSI or embedded, then electronics with minimum 60%, and you have completed course also in VLSI. So in VLSI itself, we have different domains. So you should have completed a course in any of the VLSI domain. So that is like mandatory. So after course completion, you can get directly placed into the VLSI industry. So that is the basic eligibility criteria to get into the industry. Then now we'll talk about our institute, that is Takshila VLSI. So Takshila is one of the best institute in Bangalore as well as in Hyderabad, and we provide courses like regarding all the domains in VLSI. And all these courses are for freshers as well as for working professionals. And we also provide 100% placement assistance from our part. So that may be in terms of study materials or mock interviews, resume building, etc. So in all these, we'll be providing assistance for you till you get placed. Then one of our major feature is the industry standard tools. So tools, we are actually providing it like 24/7 tool access we are providing. So as I said before, tool is very important in the designing process of an IC. So this tool access we are giving it to you means you can access it from anywhere, anytime you want. So you can keep on practicing what you are doing. So that is one important feature of our institute. Then regarding our faculty and trainers, so all of them are of 15 plus years experience, and all of them are working professionals also. So they deal directly with the industry. So once you contact with them, you also will get an idea regarding the actual industry or what is happening, what is going on in the industry. Then regarding our placement parts, we have already collaborated with 200 plus hiring companies, and they include product-based, service-based as well as startup companies. And we also provide 100% placement assistance, as I mentioned. Then we also have proven track record of placements. So regarding placements, we have like proven track record of placements with scholarship facilities. So we also have scholarship facilities available here. So regarding any of that courses or fee structure, scholarship facilities and all, you can directly contact our institute. I'll be providing you with contact details in the coming slides. So these are some of the features why to select Takshila VLSI. So as I mentioned, we provide 100% placement assistance. So be it study materials, interview part, be it placements, placement assistance. So all these will be supporting you from here. Then we also follow industry standard course curriculum. So this also we discussed, that is whatever the actual industry is following, the same design flow we are actually following here also. So the same training we are giving it, same syllabus we are following. Means when you get into the industry, that gap won't be there. So to fill that gap after college to the industry, that training is done from here itself. And then this also I mentioned, that is 24/7 lab support. Then it is low cost and value for money. So whatever or how much you are spending it here, that would be worth it once you get into the VLSI industry. So that were some of our features. So these are some of the pictures of our office. So we have office both in Hyderabad and in Bangalore. So these are some of the pictures of our Bangalore office. So you can go through the pictures. And these are also pictures from our Bangalore office. So you can see live classes are there as well as lab classes, and we have a separate placement cell also to help you and guide you through your placements. And this is our Hyderabad office. So in both offices we have live classes as well as lab class also, and placement support also will be provided in both the offices. So now we'll see a short corporate video on Takshila VLSI. So that was a short video on how life is at Takshila VLSI. So we'll move forward. And these are the different courses that we provide from our institute. So all these courses are for freshers as well as for working professionals. So first one is physical design, then we have ASIC verification, then analog layout design, design for test, and analog circuit design. So we see the different course structures and all. I mean the next slide. Sure. So this is the course structure of the five big different courses that we offer from here. So if it is physical design, DFT or ASIC verification, it is a 5 months course. It is analog layout design, it is a 4 months course. For analog circuit design, it is a 14 weeks course. So what is common is that live classes and lab access, lab class and everything would be provided for all the courses, as well as about the trainers. So all the trainers are also 15 years plus experience. And as I said, they are all working professionals also. Then we also provide 100% placement assistance. So be it study materials or mock interviews, resume building. So all those things will be covered in the placement assistance. So that also will be till you get placed. So till you get your first job, we'll be providing you with all these placement assistance as well. So now we'll discuss about some of the core job opportunities you'll be getting once you have done a course in different domains. So first one is PD or physical design. So once you have completed a course in physical design, these are some of the job opportunities that you will be getting or the job roles you can work on. So first one is physical design engineer, then ST engineer, physical verification engineer, EMIR sign off, and methodology and flow engineer. So these are the job roles you will get once you have done course in PD. Then we'll move on to the next one, that is analog layout design. So if you have completed analog layout design course, then you can work as analog layout design engineer, then standard cell layout, IO layout design, then memory layout, then RF layout. So these are some of the job opportunities or the job roles you can work on once you have completed course in analog layout design. Next we have SIG design and verification. So for ASIC design and verification, you can work at this as ASIC verification engineer, then ASIC or RTL design, then or FPGA design, then IP verification, UVM verification. So these are some of the job roles you will be getting once you complete your course in ASIC design and verification. So this one is an interesting topic, that is the salary scope of the VLSI industry. So once you get into the industry as a fresher, your salary would be around 4 to 6 LPA. So that is the starting salary package you'll be getting as a fresher in the industry. But once you have moved forward with 3+ years, then your salary also can go up to 15 lakhs to 20 lakhs per year. And you will also be getting product-based company offers as well. Then with 5+ years of experience, your salary also will come in between 25 lakhs to 30 lakhs per year. Then you can be a team lead by that time. So with the 5+ years of experience, you will be in a position where you can lead a team. Then we have 10+ years. So with 10+ years of experience, your salary also can come in between 60 lakhs to 80 lakhs per year. And you can also be a team manager with 10 years or 10+ years of experience. So that's the basic salary structure of our VLSI industry. So now we'll be talking about placements at Takshila VLSI. So regarding the placement process that we follow and regarding the placement updates of this year. So I'll be showing those slides with you. So this is about the placement support that we provide. So as I mentioned, we provide 100% placement assistance till you get placed. And that might be in terms of tools access or interview preparation, then study materials, mock interviews, everything support will be providing till you get placed. And we have already collaborated with 200 plus hiring companies, including product, service, and startup companies. So examples you can see Capgemini, HCL, L&T, Wipro, AMD, etc. And many more service-based and startup companies as well. Then this also salary package would be coming in between 4 to 6 lakhs per annum. So that would be the minimum package that you will be getting once you have completed your course. And this is the basic placement process that we follow here. So once we get requirements from the clients, so clients, they are the hiring companies. So once they have the opportunities or the vacancies available there, then they'll contact us. So once after we get to know about the requirements there, we'll assist the students in preparing their resumes. So that will be according to the requirements of the company. So once that resume is done, then we send it back to the hiring company. So different companies will have different hiring process. So that solely depends on the company. So they might have written test or they might even have many rounds of interviews. So that depends on the company. So companies shortlist from these resumes and they conduct their own hiring process. So after that, once the result is done, the hiring process is done means they'll announce the final results. So this is the basic placement process that we follow in our institute. And we'll see some of the placement updates of this year. So these are the company lists. Some of the companies that already came here for placement. So you can see some of the product companies and the well-known companies here like Qualcomm and Cadence, Digicom, Wipro, WD, L&T, Broadcom, Synopsys. So this is just a small list of the companies that we have already collaborated with. And these are some of our students who got placed into different companies in this year. So you can go through all these posters here. So two of them got placed into Cadence, that is for physical design. And this is also physical design placement as well as analog design, analog layout design. As I said, your first salary package need not be always 4 to 6 LPA. It can go up to 12 lakhs or even 20 lakhs per year. So these are some of our students who got placed in these companies like onsemi, then Synopsys and Micron, and they are for analog layout design. So we have more placement updates from this year, so you can go through all these posters. The courses they have done and the companies they have got placed, everything is mentioned here itself. You can go through each one of them. We have many number of placements in this year, so posters are also so many. Many are there in the coming slides. These are all placements of this year. You can see some companies like Siemens, Digicom, in the list. These are all placement updates from this year. As I said, all these courses that we are providing, it is for freshers as well as for working professionals. So if you want to start your career in VLSI, so this would be the best option for you. And if you are working also, and if you want to change your domain to VLSI, you can take up a course and then get directly placed to the industry. And that was regarding the placements of this year. So this is the company-wise list of the placement or the placed students of this year. So you can see majority of them got placed into Capgemini engineering this year. But not just this one company. The placement is spread across different companies. Examples you can see some of them. Cadence, Big Silica, Insights, L&T, Digicom, Apex Semiconductor. So this is the company-wise list of the placed students of this year. So this is for just to give an idea about regarding the placements and like what person got placed into what company and all. And this is our contact details. So as I mentioned, we have office both in Bangalore and in Hyderabad. So if you have any doubts regarding like courses or course structure, fee structure, placements or anything, you can directly contact. You can visit our office or you can contact through WhatsApp or email. This is our WhatsApp number and this is our mail ID. And this one is our website. You can go through website also. So our team will always be here to help you and like give you a clarity regarding all the courses and placements and all. So you can directly contact them. And in the end also I'll be providing you contact details. So you can note it down if you want now. So now we'll move forward. So again, we have some more complex topics in the industry. So that is the different design flows that are there. So before going to the design flow itself, we have to know the different types of ICs that are available in the industry now. So they are the analog and mixed signal IC as well as the digital ICs. So some examples you can see here in analog and mixed signal. So mixed signal is nothing but the combination of analog and digital that comes under the mixed signal. So these are the examples of AMS, that is simple chips, audio processing, memories, sensors also, and power. Then when coming to digital ICs, we have the complex chips, processors, wireless devices, then USB and Bluetooth controllers. So these are the different types of ICs that are available in the industry. So now we'll discuss about the different design flows. So that is the analog IC design flow and the digital IC design flow. So both of these ICs have different design flows. Like some steps are different in both the cases. So we'll discuss that both the flows. So what is common is that in analog as well as in digital design flow, we have front end and back end. So in analog, in front end, we have analog circuit design. And in back end, we have analog layout design or custom layout design. Now we'll discuss in detail the analog IC design flow. So this is analog IC flow. So whatever be the design, so be it analog IC or digital IC, we start from the specifications. So specifications can be anything. So that is provided by the end customer or the consumer. So that would contain all the functionality or all the requirements, not functionality, what requirements we are looking for in our chip. So that will be contained in the specification. So once it is done, we'll do schematic design in case of analog design flow. So this is the schematic of design. And once the schematic is done, we simulate the design. So simulation is done in order to check if all the specifications are meeting or not. The functionality is meeting, all the requirements are meeting or not, we'll check at the simulation stage. And one is if the specifications are meeting, then we'll proceed to back-end phase, or else we should go back again, redo the schematic design. And once it is met, we'll go to back-end phase. So there we have placement and routing. So that stage is where the layout of the design is formed. So this is the layout of the design. And once the layout is done, we have some checks like design rule checking and layout versus schematic. And after that, one stage is there called parasitic extraction. So parasitic extraction is where all the impurities or the noise or the non-ideal factors are added into our design. So even after that, all our specifications should be meeting. So to check that, we are doing post layout netlist simulation. And if the spec is meeting, it means we end the process, or again we should go back to schematic design and redo. So this is like an iterative process. Till the spec is meeting at our final simulation, we'll do this process. And that is all regarding the analog IC flow. And this is one example of an analog IC chip, that is the op-amp. So you might have heard of an op-amp. So this one is the schematic of an op-amp, and this is an layout. This is the layout of an op-amp. So op-amp is nothing but operational amplifier. So you might have heard about op-amp. So that is one simple analog IC, and this is the different like images at the different stages. That is the front end and back end phase at the designing of an op-amp. So now we'll move forward to the digital design flow, or we call it the ASIC design flow. So ASIC, I said earlier, that is the application specific ICs. So they are manufactured or they are designed for a particular or specific application. They are the ASIC, and they are digital ICs. So the digital design flow differs from the analog IC flow. So we'll discuss that now. First is design specification. So that stage or that part is common for both analog and digital IC design flows. And once the specification is done, we have a stage called RTL description or RTL design. So at RTL design stage, we actually convert all the specification and all the functionality and everything into a code form. So that code can be written in either Verilog or VHDL. And that code will contain all the functionalities and behavior of our design. And once RTL code is done, we should verify that if the functionality is meeting or not. So that is the functional verification step, or the ASIC verification or RTL verification stage. And once it is verified, we have the synthesis stage. So at synthesis, we are converting this verified RTL code into gate level netlist. So that will contain information regarding gates level. So different logic gates would be present to implement this functionality. So that is the gate level netlist. Then to check that, we have the logic equivalence check, that is the LEC. Once the logic equivalence check is also done and gate level is obtained, means then we have physical design stage. And physical design is nothing but we are generating the physical layout of the design at physical design stage. And this is by the process called placement and routing, or place and route. So once the physical layout is generated, we have physical verification. So we'll check all the timings, layout and everything at that stage. And then we'll end the process in GDS format. So that is the complete digital IC design flow. Step by step, we'll be dealing, we'll see the IC flow, that is the ASIC flow. So in here also we have front end and back end, as I said. And in front end we have like the designing part, the verification part, the RTL ASIC design and the verification, as well as DFT. So DFT is designed for testability. So we'll see that in the coming slides, DFT in detail. And in backend, we have physical design and physical verification. So now we'll discuss each step by step in the digital IC design flow. First one is specifications, as we discussed. So specifications can be anything like the size or the speed, then power consumption or anything. So these are some of the examples of the specifications. And that is provided by the end customers or the consumers. And once the specification is done, then we have the architecture design. So architecture is designed by a separate team, that is the architecture team. they convert specifications to the architecture design. And that can be in any form like plot diagrams, flow charts, or spec sheets. So that is about the architecture part. Then once it is done, we have RTL design. So RTL is nothing but register transfer level. So that, as I said, it is a code that is written in either Verilog or VHDL. And this code will contain all the functionality of our design. So this is one example RTL code. So this code will be describing how data is transformed as it passes from register to register. So that is the register transfer level or RTL code. And once the RTL coding is done, then we have to verify if the all functionality is meeting or not. That is at the verification, the RTL verification stage. And this is about RTL verification. So in RTA verification, it is like a black box testing. Like whoever is testing, they won't know what is inside the design or what functionality is it performing. They just provide all the possible test cases. And so that if all the test cases is passing and if all our result is matching with our expected results, then we can say that it is functionally verified. So we have something called coverage analysis here. So in all the possible scenarios our chip can work in, like in all the different possibilities, all we check design and we need to verify that it is perfectly working, functionality is meeting or the specifications are meeting and everything. So that is done in the verification stage, and design under test is our design that we are currently testing. So we can do it in full chip form or we can divide it into different blocks. Only thing is that we have to check and verify each and every block in our design. And if it is not meeting, not matching with our expected results, mean we should go back again to test plan and we should check for more test cases, edit test cases, and we should finally verify the whole code. That is the RTL verification step. And once the verification is done and the code is verified, means we have the synthesis part. And then in synthesis part, we are adding the DFT. So we'll discuss about that. So DFT is designed for testability. So it is nothing but we are adding an extra logic to our normal design so that we can add a testability feature once the manufacturing of the IC is done. So the post-production testing is actually done using this DFT. So it is necessary because our manufacturing process need not be 100% error free. So because we are dealing with very small range of like nanometer ranges we are dealing with, and silicon defects might be there or impurities might be there or something might go wrong in the manufacturing stage. So after that, to check our chip, we are using this DFT technique. And this extra logic we are adding it in a normal design at the designing phase itself. But this extra logic we are only activating it once the chip is manufactured completely. So after that we are testing the chip if it is working. Like many techniques are there to check the chip. And once it is done and if it is okay, then we'll release the chip or we'll give it to the customers or consumers. So that is how DFT is done. And DFT is like one of the most important domain in VLSI nowadays. This is all regarding the DFT. This is the basic introduction to DFT. And once our synthesis is done, then we have physical design. So physical design also has different steps. And in physical design, as I said, we are generating the physical layout of our design. So these are the different steps to generate the layout, that is partitioning, floor planning, placement, CTS, signal routing, and timing closure. We'll discuss it one by one. Yeah, so physical design, as I said, we are generating the layout at this stage. So the main aim of the physical design engineer is to design the layout with minimal area. So area should always be minimized. So that is one major factor when it comes to physical design or the layout part. Like it is better if we can implement all the functionalities in a much minimal area. So that is the main objective or the main aim of a physical design engineer. So the physical design process is actually fully automated process. Like as I said, the tools are there. So all these tools will be generating the physical layout, but we have to give certain input files. So as we give the input files, tool will be generating the layout automatically. And these are the input files for physical design stage. So that would be gate level netlist from the synthesis stage. Then we have constraints, then logical and physical libraries, then depth, canvas and UPF. So these are some of the input files that we are giving to the physical design stage so that the tool can generate the layout. And this is how it will look like once we load the design. So this is some tool interface. So this would be the boundary of our chip, and this would be macros or the memory elements. And these are all cells, the standard cells in our design. So all these things will be arranging it inside this boundary, so that once it is arranged and perfectly done, that is called the layout. So that layout generation is done at the physical design process. And first step is floor planning. So floor planning is when we decide the boundary, the core area and everything. So it can be done in full chip form or block level form. So full chip means if this is our whole chip, then we can decide the area of this chip, then how to place macros or the memory elements, how to place them here. Then regarding all the ports access. So all these things will be doing the floor planning, and this is for full chip. But if the chip size is very large, and if one person or one team cannot do floor planning, means we divide the whole chip into different blocks. So that is block level floor planning. So if this one is the whole chip, we can divide it into different blocks. So this might be one block, this might be one block, this might be one block. So different blocks can be designed by a different team or an individual. So some of the steps are same, or steps can differ, but all the placement of macros, the codes, so that are all same process in the full chip and block level floor planning. So once the floor planning is done, we have power planning. So that is when we are placing the like straps for VDD and VSS, the supply and ground to our design. That is the power planning stage. And this is one example of a core limited die. So this is our core, and inside this core, we are placing all our standard cells and our macro cells. And you can see the power ground connections straps here, as well as the IO cells. So they are the input output cells, IO pads, everything. And this is how it will look like once the floor planning is done in the tool interface. So this is our boundary, and you can see all the macros have been placed inside the core, and it is always placed towards the boundary. And the center area is actually left for placing the standard cells. So these are our standard cells. So everything we'll be placing it inside this area at the next stage, that is the placement stage. So placement stage is nothing but we are placing all our standard cells inside our core area. So these are our objectives, our main aim. So less utilization jump should be there. Then there should be no congestion or overlapping or any legality issues. And then we should have good timing values. So once the placement is done, we'll see how it will look like. Yeah, so this is how it will look like. So before we saw that this area, the center area was completely empty. But now all our standard cells got placed inside this area. So that is done at the physical, the placement stage. So tool will be placing them automatically as we give the scripts, as we run scripts, tool will be doing this process automatically. Once the placement is done, then we have CTS, that is clock tree synthesis. So clock is one of the most important signal in our whole design. So as we are dealing with sequential cells, all sequential cells needs clock to work or to be active. So when we are transporting or transmitting clock, if suppose this is the clock source, we are giving this clock to say this cell, we should make sure that clock is reaching correctly to all the cells. And if we are transporting it to different cells, means we should make sure all the cells are getting the correct clock. And ideally, it is said that a clock has to reach at the same time to all the cells, but practically that is not possible. Some delay difference would be there depending on where this cell is situated. So that delay difference is called the skew. So to minimize the skew and to make sure that clock is reaching correctly to all the cells, we are building something called the clock tree. The clock tree is built using buffers or inverters. So this is the clock tree. So clock is passed using this clock tree. So this looks like a tree structure. That is why we are calling it as clock tree. And then we are passing this clock to all the sequential cells. So these are all our cells, sequential cells, or the end nodes. And these branches are called clock spines, and this mesh is called clock mesh. So mesh wise or like tree structure wise, we can build our clock tree, and clock tree building is also done by tool itself. Once we run scripts, tool will be generating the clock tree. That is about the CTS part. After CTS, we have the routing part. So routing is nothing but where the all metal connections that are there in our design, that is been formed. So before routing, no metal connections would be made in our design. So at the routing stage only, all connections are made. So that connections may be between standard cells or macro to cells, then ports to cells, or all kinds of connections that are there in our design, that would be made at the routing stage. And routing also has different steps: global routing, track assignment, detailed routing, and search and repair. So in global routing, it is like an imaginary routing. Actual routing is not happening there. During global routing, tool will decide through which the route should happen, and which will do the routing imaginary way. After that, we have track assignment. In track assignment, also actual routing is not happening. It is also like an imaginary routing. Tool will decide through which track each route should happen, and all those things. After that, we have the detailed routing. So only at the detailed routing stage, the actual metal connection is being made. So all the connections in our design would be made at the detailed routing stage. And once it is done, we have search and repair. That is the last stage of routing. So during search and repair, like they already made routes. Tool will check like based on all the like wire length, area, power, and things. If any route needs any repair, means that is done at the search and repair stage. So that is regarding the routing stage, and with that, physical design process also comes to an end. And once the physical design is done, we will get the physical layout of our design, and we should verify the layout. So that is the physical verification part. Yeah, so this is the verification part, and that is also called sign off. So during sign off, we have different types of checks. So some of them are like formality checks, then layout versus schematic, design rule checking, timing analysis, design rule violations, then IR drop analysis. So these are some of the checks that we do at the physical verification stage or the sign off stage. And with that, our digital IC design flow also comes to an end. So that was the whole of today's webinar. So if you have any doubts regarding any of these topics, like regarding the design flows or even regarding our institute, you can ask me. You can unmute yourself and ask, or you can put in chat box also. Doubts regarding anything, you can ask, or we can wind up the session. Yeah, so we'll wind up here. So that was all regarding today's webinar, and thank you. So our HR will be giving the vote of thanks now.
Good evening. A heartfelt thanks to Ms. Neha ma'am for sharing their valuable insights. I would also like to thank the HOD and students for their efforts in making the webinar a success. Looking forward to more such interactions. Thank you.
Yeah, regarding the PPTs, we'll share it with your HODs once we discuss it with our manager here. So if you have any other doubts, you can ask, or we'll wind up